So, what actually happens when the entire world suddenly, and I mean seemingly all at once, decides it desperately needs artificial intelligence? It's kind of the defining question of our time, isn't it? We aren't just talking about a cool new app on your phone or a slightly faster laptop. We are witnessing a fundamental, ground up rewiring of global infrastructure. From those massive, humming data centers out in the desert to the complex software being written by developers right now, the AI revolution is sending absolute shockwaves through literally every industry on the planet. Okay, let's dive into this. According to a massive 2026 report by PwC, the global semiconductor market is projected to cross a staggering milestone, $1 trillion. Let that sink in. By 2030, the very physical building blocks of our digital world will make up a $1 trillion market. That is a mind-bending scale, and honestly, it completely reshapes how we need to think about the economy going forward. Welcome to this explainer, where we are going to unpack exactly how all of this is happening. We're exploring the foundational layer of this massive tech boom. We'll start way up high with the macro market data, the sheer volume of hardware being produced, and map that all the way down to the micro-level reality of software engineering and everyday industrial applications. It is a fascinating chain of cause and effect. Here's our clear roadmap for today. First, the trillion-dollar chip market. Second, designing the AI future. Third, the reality of AI coding. Fourth, industry transformation. And finally, power, pricing, and the quantum horizon. Starting with Section 1, the trillion-dollar chip market, the hardware bedrock. Because at the end of the day, you simply cannot have artificial intelligence without the physical silicon to process it. Think about this incredible projection for a second. We're starting from a baseline of roughly $0.6 trillion back in 2024. To reach that $1 trillion mark by 2030, the overall semiconductor market is growing at a massive 8.6% compound annual growth rate. That's a relentless, heavy-duty expansion across the entire global supply chain. But, when we look a little closer, we see that not all chips are created equal in this boom. And this brilliantly illustrates exactly where the heat is. While the overall market hums along at that 8.6%, the server and network chip sector is just surging ahead at an 11.6% annual growth rate. Why? Generative AI. Those massive data centers required to train and run large language models are uniquely supercharging the demand for high-performance processors and memory well above the baseline. Moving to Section 2, designing the AI future. The tools for next-gen chips. Because before any of these chips can actually be manufactured, they have to be designed. And AI chips are frankly some of the most complex structures humans have ever engineered. Just look at Cadence Design Systems. They're a major leader in electronic design automation, or EDA. Their Q1 2026 numbers are absolutely explosive. We are talking $1.474 billion in quarterly revenue, and 18% growth in their core EDA revenue, and a record-shattering $8 billion backlog. These numbers are a direct, undeniable reflection of the global scramble to design the next generation of semiconductors. You know the old saying, right? In any gold rush, the surest bet is usually the company selling the picks and shovels. Well, EDA tools are exactly that. Cadence's massive $8 billion backlog is directly driven by this intense, unyielding demand from AI and high-performance computing customers. Literally everyone is trying to build a better, faster chip, and they all absolutely need these software tools to pull it off. Let's jump to Section 3, the reality of AI coding, moving beyond the hype. So what actually happens when we shift from hardware design to the software developers who are using AI to write code? Now, what's really interesting about this is the stark contrast between marketing hype and actual hard data. AI coding vendors love to throw around claims of 10x productivity gains. It sounds great, right? But the 2026 benchmarks from Laridan, which actually analyze real AI-native engineering data, they show a reality of a 1.6x ROI. Now, don't get me wrong, 1.6x is a distinctly positive return, but it really forces engineering leaders to realize this isn't some magic wand, it requires serious management. The absolutely crucial point here is understanding the hidden costs. Laridan's data highlights that code churn, which is code that gets rewritten or deleted shortly after being generated, has risen to between 5.7 and 7.1%. Plus, teams using advanced agentic tools, AI that kind of acts autonomously, are spending anywhere from $200 up to $2,000 per engineer every single month just on the compute tokens required to power them. So yes, AI generates more code much faster, But if that speed comes without quality gates, you are just compounding your expenses. Section 4, transforming every industry, beyond the tech centers. Because these powerful new chips aren't just sitting around in Silicon Valley server farms, they are rippling outward and transforming the entire global economy. To really ground these abstract numbers, consider the physical, everyday applications. On one hand, you have incredibly advanced surgical robots that require intense, localized processing power to operate with microscopic precision. On the other hand, you have specialized embedded microchips being integrated into almost every physical device we manufacture today. This semiconductor boom is a very tangible, physical reality, not just a digital one. Let's move on and see how this builds across entirely different sectors. Smart agriculture is projected to grow at an unbelievable 17.3% annually as farms become heavily digitized. Renewable energy is surging at 13.4%, primarily driven by the need for smart power grids. Semiconductors are no longer just for computers, folks. They are basically the central nervous system for agriculture, energy, automation, and medicine.
Finally, Section 5, Power, Pricing, and Quantum, the limits and the horizons. Because as we know, you can't scale indefinitely without eventually hitting a wall.
In the world of chip design, there is this ironclad law known as the PPA triangle. It stands for performance, power, and area. As AI demands unprecedented performance and engineers desperately shrink the area of these chips to pack more in, well, the power consumption and the resulting heat is absolutely skyrocketing. We are quite literally pushing the very limits of physics and thermodynamics here.
And hey, pushing physics? It is incredibly expensive, $18,000. That is the staggering cost of just a single cutting-edge 3-nanometer wafer from TSMC today. We're talking silicon engineered at the atomic scale. That price has tripled in just 10 years. As the fabrication processes become more and more exotic just to keep up with AI's demands, the pricing pressures on the entire industry become extreme.
So what is actually on the horizon? The PwC matrix outlines two massive tectonic shifts coming our way. First, partial artificial general intelligence, or AGI, is expected with an incredibly rapid 2 to 5 year timeline. That's going to drive even more intense semiconductor demand. Looking further out, quantum computing stands as this massive long-term game changer. It's poised to revolutionize fields from encryption to drug discovery by processing information in ways that our classical chips simply cannot do.
Which brings us to one final, really provocative question. We've seen the trillion-dollar projections, the incredible design tools, and the transformative potential across every single industry. But as these AI chips get hotter and much more power-hungry, the cooling and electrical demands are becoming astronomical. We clearly have the technology to build the future, but as we look ahead to 2030 and beyond, do we actually have the power grid and the cooling capacity to keep it all running? Definitely something to think about. Thanks so much for joining me on this explainer, and as always, keep learning.